Yes, well, thanks very much, Chris. Firstly, to the Society, many thanks for the invitation. It's a great thing that we do now have societies meeting and communicating by electronic means, such as we're doing tonight. It's obviously a shame that it took such a terrible thing to get us all going in this mode. So yes, I've given talks to probably the nearest ones to here would be based in, the nearest ones to Hereford would be based in Kidderminster or Knighton in Wales, but this enables me to just get that little bit further south to Hereford. So thank you for the invitation. It did get me thinking that, yes, it's probably 1984 since I was last in Hereford, so at least I've got an electronic presence in Hereford here tonight.
If you came now, Colin, you wouldn't notice the difference, I have to say. It probably still looks like it did in 1984.
Ah, yes, I'll have to test that one out sometime. But yes, Coronal Conundra and Prominence puzzles. Let's start off with what happens to the sun at the beginning of the day. Yes, rises, in this case, out of the sea somewhere. Now, I have to confess that this one was taken through a double glazed window, and you can probably tell that one. I have fewer sunrises than I do sunsets, but the beginning of a day seems a good thing to mark at the beginning of this talk. Now, we're talking about the sun here. What can we say about the sun? Or put it another way, if the sun was a person, what would the identicard of the sun actually say? So obviously name, sun, address, well, the Orion arm. Age, well, the sun has been around for quite a long time. Height, the sun is, in linear terms, 100 times the size of the Earth. So in terms of volume, it's a little bit over 1 million times that of the Earth. And yes, when you see waistline and weight, I start to feel slightly less bad about what I have accumulated. The temperature of the sun, well, there's an interesting tale to be heard here. In the center of the sun, the core, we're talking about 14 million Kelvin. Now, the difference between Kelvin and, well, centigrade or Celsius, and between the two scales is less relevant once you get up to the millions. But on the coolest part of the sun, the surface, which is at about 6,000 degrees, the 273-degree difference between the two scales is just about starting to come into play. But the interesting thing is up in the atmosphere. Well, we'll come to this, but you have a higher temperature up in the atmosphere than you do on the surface. What else do we say? Occupation. Converting hydrogen to helium, producing energy, providing gravitational field for the planets and the comets and so on to go around. And then distinguishing marks. We have that on an identicard, but interestingly, in the case of the sun, if you were to chance on a conference about the sun, there would be not a great deal about what we've just discussed, the main characteristics, but the distinguishing marks would really take up all the time. The fascination about what can be seen to be some minor features, but are delightfully interesting things in their own right. So I've mentioned a list of them here: sunspots, prominences, faculae, loops, coronal mass ejections, solar flares, and indeed there are many others. And yes, the actual type of star that the sun is, G2V. Well, really what this means is that it's a main sequence star the G, in particular the G2, yes, it's towards the cooler end of the main sequence in the effective yellow area. So, that is the sun. It's drifting with respect to some of the other stars in the direction towards Hercules then. So that's a little bit about an introduction to the sun. But let's go through the structure of the sun. If we're talking about, if we go from the center of the sun to the outside, if we did something similar on the Earth, we'd go from the core through the mantle to the crust. On the sun, again, we've got layers there, but it's a very different story here. But we start off in the middle of the sun, the core, which is about, as you can see, it takes us a quarter of the way from the center out to the edge here. In the center of the core, when the sun is at its hottest, we are talking about 15 million Kelvin. At the edge of the core, yes, around here, we are talking about 8 million. So there's a difference of 7 million Kelvin, and heat being what it is, it flows from the very hottest part in the center over to the edge of the core and then onto the parts beyond. So the next part that I've given in an orangish sort of color, radiative zone, heat is transferred through radiation, albeit very slowly. Heat does not radiate very far before it bumps into another atom there. So it can take heat that is created in the center of the sun. It might take thousands of years to make its way through the radiative zone. And again, by the time we get to the outer edge of the radiative zone, the temperature is down to about 50,000 Kelvin. There comes a point where radiation becomes less important in the transfer of heat, and you've now got convection. So heat is transported in terms of circulation in cells. Gas gets heated up, and that hot gas or plasma moves itself further out, passes the heat on to the next stage, and then goes back down again to get some more heat. So by the time we've got to the outer edge of this convective zone, we're down to about 6,600 degrees. And then I've used the color green, but it's not really green. The photosphere, that is the nearest thing that we have to a visible surface for the sun. It's quite a thin layer, 500 kilometers in width. So if you were to take, a typical country such as the UK and put it endwise into the photosphere, it would stick out at both ends. Of course, I'm not suggesting such a terrible action there, which of course the country would not survive in any form at all, even the journey to there. But the whole point is, yes, the photosphere, you've got the sphere of light here, and at the outer edge of that, we're down to about 4,300 degrees. And that is the coolest temperature in the sun. The photosphere is regarded as the surface of the sun, but it's also regarded as one of 3 atmospheres that the sun has. The terminology is different from the Earth. In the Earth, we have an atmosphere, and we have several layers to the atmosphere. The sun is generally thought of as having several different atmospheres. But the one above the photosphere, that is the chromosphere, the sphere of colour, and you can see, well, our cooling temperature, the trend seems to have been reversed here. And it's about 4,300 degrees at the bottom of the chromosphere, it goes up to about 1,000,000 Kelvin at the outer edge of the chromosphere. So there's a bit of a mystery there that I will be touching on a little bit later. How does the heat get up this gradient here? It seems to go against the second law of thermodynamics. And then the final section of the sun, the corona. It extends indefinitely in that you go further out and it just gets thinner and thinner rather than having a particular outer border there. But the maximum temperature that you get in the sun's corona is about 5,000,000 degrees. So that's something about the structure of the sun. But we can ask the question, well, what is the sun made of? We're familiar with solids, liquids, and gases, and I've listed some of their properties there. Generally, gases exist at hotter temperatures than liquids, and even more so for solids. Gases are effectively a situation where the molecules move independently from each other. But we can actually take this a little bit further and consider the fourth state of matter, a plasma. So rather than having atoms, the atoms have broken up. There's so much energy and everything is so hot that the electrons are able to escape from the atoms. So you've got the whole thing made up of various ions and electrons. So this gives the plasma the ability to conduct electricity and respond to magnetic field. So the sun's corona is, for the most part, it's not made of gas. We often think of it as gas, and of course we can ask the question, does plasma form a subset of gas? But plasma is what the solar corona is actually made of. Now, when we look at the sun, we can, of course, well, I'll come to looking at the sun, but when we observe the sun, we can observe in all sorts of different wavelengths, and we can see that the general legend of the sun being a big ball of gas isn't quite true, in that look at the number of features that we have here. And we have another one here. There is all sorts of structure to the sun here. Now, obviously, I'm not talking about the fact that Venus happens to be passing across the sun at this point, which is a very rare thing to happen. It will not happen for another century. We had our chance, or two chances, in fact, not too long ago. But there's all sorts of structure there, and this is a structure of not solid objects or anything like that, but the magnetic field. The plasma responds to magnetic field, and it has a great deal of structure there. So let me say something about magnetic fields. We often represent magnetic fields by means of arrows. Lines and arrows, and where the lines are close together, we have strong magnetic field, as in on the left here, and where the lines are further apart, we've got weak magnetic field. Now, it's tempting to think of magnetic field lines in terms of elastic bands or something similar, and in some cases, that's not too bad an analogy here. So we have strong field and we have weak field. And one thing that this does is if you have changes in position of the magnetic field strength, this produces a pressure force. So plasma will be forced from the strong field to the weak field. So we have a magnetic pressure force, but we also have, and this is where the analogy of the elastic band really come into play, that if your field lines are curved, this is going to introduce a magnetic tension. So possibly when you're seeing this one, you've started to think in terms of catapults, and it works in the same way. We would have a tension force to the left due to field lines, the curved field lines. And it might be that you've got a situation where the field lines are curved in one particular direction, but you've got a difference in the field strength, which exerts a pressure that equalizes the tension from the curved field lines. And if the magnetic field stays in this configuration, then the plasma will stay at this point. It is in equilibrium. Now, I hinted about, yes, observing the sun. Observing the sun is not a trivial matter. It is not a case of point your telescope at the sun and look through it, like is the case for virtually every other astronomical object. With most astronomical objects, when you observe them, what you're trying to do is gather as much light as you can. But with the sun, it's the opposite. You've got enough light, and effectively you're trying to cut down the amount of light that is arriving from the sun. Specifically, you're actually trying to cut down on the amount of heat, because if you were to be unwise enough to look at the sun through a telescope, you would risk doing irreparable damage to your eye. The safest way to observe the sun is by means of a setup like this, where we have a piece of card held behind the telescope, so the image of the sun, shines onto the card here. It also has the advantage that several different people can observe at the same time. You know, I've been at various situations where if there's a single telescope and it's pointing at, say, the Orion Nebula, you've got one person observing who finds it difficult to tear themselves away from that. But on the other hand, you've got a queue. But with the sun, people can gather round in different directions and look. So the idea of projecting the sun onto, well, it doesn't even have to be a bit of paper. If you've got your stonework or a building, you can use that. Now you can carry out, if you have appropriate filters, you can carry out observing of the sun using those filters, but I encourage extreme caution for this one. There are good filters and there are slightly less good filters and so on. So I would say you do get to know about any use of filters along with an experienced observer, someone who's experienced using them. And then, of course, you'll get the experience and so on. But obviously, if something goes wrong with your eye due to a filter failing at a particular time, and of course, if it's a large filter that goes over the main lens or mirror of a telescope, then that's one thing. But if it's a filter near the eyepiece, that's possibly a bit more vulnerable. If you observe photographically, then you will be able to, you won't be taking the same risks, or rather you'll be taking the same risks with cameras and other equipment that, well, it still is expensive, but it can be replaced. But when we see here, we do note something like this. We do have a feature on the sun here, and this is a sunspot. Here's an example of a filter being used with, well, it's not a telescope, it's a 500mm lens here, pretending to be a telescope here, but we've got the filter over the lens, and yes, this gets rid of an awful lot of the light, and in particular the heat from the sun. Sometimes when you observe with fairly small equipment, yes, you're not able to see a great deal on the sun, but observing with bigger instrumentation, you can see really quite a lot here. Here we have an image. Well, it's a series of images which have been put in over a period of a few days. One thing, that it does seem that the sun is rotating, but we do have significant features, significant sunspots here. Another thing to note is that, yes, sunspots are seen near the sun's equator, but generally in bands to the north or south. Often you'll end up seeing the sun at all sorts of funny angles here, but we can see that sunspots do often appear in pairs or in groups with two main spots there. And this is all due to the magnetic field. If you look at a sunspot closer up, well, one thing to say is, yes, an image, a circle has been put here, which is the approximate same size as the Earth. We are talking about sunspots being of comparable size to the Earth. So that's one to think about. We see that the sunspot, each sunspot seems to have a dark area in the center that we call the umbra, and then maybe a fibril type area, less dark than the umbra, but darker than the surrounding parts of the sun. We call this one the penumbra. And the concept of the umbra and the penumbra link in with magnetic fields. Now, the sunspot appears dark here, particularly umbra. But let's just say, if, again, we're considering a totally unrealistic experiment in astronomical engineering, if somehow we were able to extract the sunspot itself and just take it to the night sky and put it at a comparable distance from the Earth that the sun is, so out somewhere probably towards the asteroid belt, that little bit of the sun, although it appears dark here, it would appear about as bright as the full moon. So they only seem dark because they're surrounded by even brighter things. And again, the umbra and the penumbra, you've got some quite remarkable pictures here. Oh, this is one that I put in. I filched this one off NASA's Astronomy Picture of the Day site. Effectively, you can see sunspots in what's the sun in a more leisurely situation here between the trees. But it is thought that a sunspot looks a bit like this. You've got magnetic field coming out from the sun, and it spreads out once it gets through the photosphere. Now, the sun's magnetic field is not like that of the Earth. On the Earth, the magnetic field plays a quite reasonable approximation to a dipole field. On occasions, the field is perturbed, and we can get things like aurora there, but the sun's magnetic field is extremely complicated with bits going in and out everywhere, and often when you have the magnetic field emerging from the solar interior, or indeed going into the interior, which it would do so with the arrows reversed here, then this manifests itself in a sunspot. So you can see here, dense field in the center, the umbra, less dense field in the penumbra, the surroundings. Now, this is a picture of the sun taken on the 1st of March, a few days ago. So let's just see what's happening. We've got, a few sunspot groups, various places around the center of the solar disk. But let's just move forward over the next few days. So 1st of March, 2nd of March, everything's moved to the side. 3rd of March, it's moved again. And you can see we've got new stuff coming over the limb here. 4th of March, 5th of March, the stuff that was near the center is now approaching the opposite limb. 6th of March, if I'm correct, this is the one that was earlier today, around, midnight at the beginning of today. And then there was one more that was taken at about 6 o'clock here. So it's not quite the 7th of March, 6.75, but you can see here that, yes, you've got over the course of a few pictures, everything moving to the side. The sun is rotating. Now, sunspots do evolve themselves over this time, but they follow the rotation of the sun. So sunspots, when they disappear off the edge of the sun, off the limb, you can see we've got, over the last few days, we have this group of two approaching the limb, and they were barely visible today, so close that they were to the limb. It's possible that in a couple of weeks they will emerge around the opposite limb, around here, where the other features were emerging there. So sunspots can last a few rotations of the sun, or they can disappear and be replaced by other sunspots, and so on. Now those pictures suggest that the sun rotates, about a quarter of the way in about a week, but it's actually a little bit more complicated than that. Once again, I'm going to be considering an unrealistic experiment in astronomical engineering, and that is to take the sun and to paint a red line from the North Pole to the South Pole. And on day 0, our red line here, it can be seen. And, the sun is rotating. So a couple of days later, it's moved over to here. By about day 7, it's just disappearing off the limb here. It goes round the back and not much is visible for a few days, but maybe around day 22, it starts to reappear. And around day 27, on the one hand, we could say it's moved back to where it was, but not all of it. Well, firstly, the part near the equator has rotated once around the sun in those 27 days. But do bear in mind, after 27 days, the Earth has moved almost a 12th of its journey around the sun. So it's actually observing from a slightly different viewpoint here. So the sun actually, the equatorial part of the sun rotates in about 25 days, But the regions further from the equator, well, they are rotating more slowly, and they can take up to about 34, 35 days to move around once. Well, the sun is not, it's clearly not rotating like a solid body. And of course, we wouldn't expect it to. We've already discussed that it's not solid there. We can see what's happening at various depths, and it does seem that the inner half, 2/3 of the distance from the solar interior to the surface is more rotating like a solid body, but you've got different behaviors at different latitudes for the outer parts. This is a little bit speculative, and people, of course, are just finding out more about this. Now, not only do the individual sunspots come and go, they're replaced by others, but over the years, the number of sunspots does seem to vary. We can see here the number of sunspots over the last couple of hundred years, and there is a semi-regular cycle here. It's often something that can be used to define a semi-regular cycle. We've got a situation that some peaks are higher than other peaks around 1800. Some peaks occur closer together in time than other peaks, but you've got this rough cycle that's taking place. And yes, in the last couple of years, we have been going back up towards solar maximum. But what actually happens over a solar cycle is near minimum, there's not too many sunspots, but then more sunspots appear at the higher latitudes, about 30 or 40 degrees. And then over the solar cycle, as sunspots get replaced by other sunspots, they do seem to be occurring closer and closer to the equator. So at the end of a cycle, when there's not too many sunspots left, the whole thing, the sunspots that do exist are near the equator, and they can be joined by other sunspots from the new cycle at higher latitudes. The other thing to say is that each sunspot cycle, when it gives way to the next cycle, the polarity, the magnetic polarity of everything is reversed. And when you look at several of those together, you can see why this is often referred to as a butterfly diagram. But it's not just sunspots, it's all kinds of solar activity over the course of a sunspot. If we look at the amount, generally the amount of energy in the sun's atmosphere, it increases up to solar maximum and then decays away, and then the next cycle will come. But interestingly enough, when we look back at 400 years rather than 200 years, something interesting seems to have happened in that in the 17th century, there were not many sunspots at all. Now, shortly after 1600, that's when Galileo was observing. He observed sunspots, drew people's attention to them. One interpretation is that, yes, he drew people's attention to them and they observed for a bit, and then sunspots became old hat for about 50 years. But after 1700, people really did start taking an interest in them again. But it's thought it is a real effect, not just a lack of observing there. You can also find various correlations in non-sunspot things, like the strength of annual tree rings. It would seem that around that time, there were no sunspots and the climate was slightly different. So this period It's known as the Maunder minimum, and temperatures across Europe were slightly lower. And indeed, there are various recordings. The one I found about Hereford was that, yes, 1683 to 84 was a particularly severe winter in Hereford, and that the river may have frozen. Other parts of the country have probably got some more exact statements having been made, but it's a case of the mini ice age of the 17th century did seem to coincide with a lack of sunspots there. We can ask the question, were there any earlier Maunder minima? And it seems that, yes, Maunder minimum around 17 whatever seems to have been the most severe one, but we're looking at something involving carbon dating here, but it does seem that there were a few, perhaps not quite so severe minima over the centuries leading up to that point. Of course, all sorts of people have tried to correlate various things about the solar cycle, car production in various factories, various things to do with the weather. I did ask a well-known piece of software, are there any correlations between the sunspot cycle and events in Hereford? And this is what it came up with. Flooding effects may be more at solar maxima. And then we've got the various military places based around that may have been more active around solar maxima, and also a sporting one here, but it does refer to this as a fun, light-hearted coincidence there. So make of this what you will. Sometimes those pieces of software effectively just end up telling you what it is that you want to hear. Now, one thing that the sun does over the course of a year, it moves once around the sky along the ecliptic. Over the course of a month, the moon will move around a band which is centered on the ecliptic. So each month, the moon will pass the sun. Sometimes the moon will pass to the north of the sun, sometimes to the south of the sun, but occasionally the moon will pass in front of the sun. On some occasions, it's not a perfect lineup, and the moon will block out part of the sun, but on other occasions, the moon will pass directly in front of the sun. If you're going to just sit in a place and wait, then it could be quite a few centuries before this phenomenon, a total eclipse of the sun, comes your way. But if you're prepared to travel, then yes, there is generally, on the time scale of once every year or two, there is a total eclipse visible from somewhere on the Earth. So this is one that, well, it's actually quite a long time ago now, 1999, that those two photographs with different exposure lengths were actually taken in Munich. But we can see some perhaps better photos of the sun in the eclipse. When the sun is eclipsed, you're able to see the corona, the outer atmosphere of the sun that I mentioned. This one's cheating a bit. It's actually two photographs put together, one just when the sun was going into totality and one as it was coming out. But a few photographs of various solar eclipses here, and the fact that at different times in the solar cycle, you can have the corona taking on different shapes. Sometimes, if the moon is out near the further part of its orbit, then it's possible that the moon will not be large enough in angular size to cover the sun, and we have what's called an annular eclipse. So a few more eclipses here. There's one that was seen a few years ago from USA. It was never going to be total in UK, but this is the view that we got of the partial phase there, possibly something we would have expected there. So total eclipse of the sun, I would recommend that, yes, it is worth traveling to at least one just to be able to experience this. There is, of course, going to be a partial solar eclipse later on this month. So, and then it's going to be a lunar eclipse as well. The two do occur generally a couple of weeks apart, but you'll observe safely the solar eclipse that's coming up later this month. But sometimes you are able to see, when it's an eclipse of the sun, you are able to see some features in the sun's atmosphere. Large amounts of cool material, I mean a mere 10,000 degrees in this corona, which is at 1,000,000 degrees. So we've got here large amounts of cool material in the corona. They can appear, well, here they appear bright against the darker surroundings, but when you see them against the disk of the sun, they would appear dark, and they are associated with magnetic field. Sometimes they'll show a complex fibril structure, and sometimes they'll show some strange shapes, such as what we can see here or here. So prominences, they have been called the equivalent of clouds in the sun's atmosphere, but there's so much more to them. They can last up to a period of months, and you can see the dimensions that they take. So they can be as thick as the Earth, but much longer and much higher. And sometimes, as you can see, they do erupt off out into space. So prominences, they raise some questions here. I say unanswered or partly answered questions. Firstly, how do they form? A cool area does not naturally condense in a hot region. An equivalent of that saying is pockets of liquid nitrogen do not form in the desert here. So that's one question. How do they form? How are they supported? They just remain suspended above the solar surface. Why does the cool, dense plasma not fall to the photosphere? We're well aware what happens here when the clouds get too heavy. And a third question, well, why do they erupt? If they just exist for months, why suddenly erupt? Our clouds don't go off erupting into space. So that's a few questions about prominences. I could go on for hours about the answers to them, but I'll try and keep things brief there. But just looking at some of the questions here, why might they form? Well, sometimes we can have a situation that, well, normally we would expect the hotter something is, the more it would radiate. But just occasionally you can have situations that the hotter something gets.
Who do you want to speak? Philpotts? They sold the house in 2009. Sorry. You remove them for your database. Okay, bye.
Okay, if we have a situation where normally the amount that something radiates increases when it gets hotter, but depending on all sorts of things to do with ionization and so on, it might be that if something gets hotter, it starts radiating less. And if it's still receiving the same amount of heat, it's going to get hotter still. Or if it gets cooler, which is perhaps the more relevant one, and it actually starts radiating more, it will become even cooler. And this may result in a situation where things cool really quite quickly. We call this thermal instability. So this may be a reason for prominences to form. How are they supported? Well, generally, it's thought they are supported by the magnetic field. The magnetic field, if the magnetic field contains something of a dip here, you can see in this green area, we've got something of a dip here, and there's going to be an upward magnetic tension force. So that, it would seem, is able to counteract gravity and support the prominence. Why do they erupt? If they exist for months, why suddenly erupt now? Well, it's a case of we can create a model, do some sums, and we find when we solve things that you can have slowly things change, but yes, slowly things change, but over a longer period of time, you might find the prominence is maybe getting slightly higher, but there is a limit to how high it can go and remain in equilibrium. And once it reaches that height, it can go off, it can erupt off out into space. Okay, so something else that I touched on, the coronal heating question. You can see that we've got the solar interior at the bottom here. I've turned it into a rectangular geometry here. 15 million degrees, and heat flows from the hot interior to the cool photosphere. But then it seems counterintuitive. Why does it flow out to the corona? We know that it does, because if it didn't, then the corona would cool, and perhaps more relevantly, we would cool. So we do need to ask this question, why? What heats the corona? Now, all sorts of theories have been produced, but there's not general agreement about this one yet, but it is thought that, well, the one thing everyone agrees on, we'll call it the coronal heating question. That's just about the only thing that people do agree on. There are, many people think it is to do with solar flares. You've got areas of the sun that suddenly become much, much brighter. Those occur at the level of the photosphere, but somehow energy must travel, perhaps up the field lines, in order to heat the corona. Again, we can see here we have rapid change here, when something is causing part of the sun briefly to become much brighter. Well, it is thought that there's a process known as reconnection, which releases energy. Let's go back to our magnetic fields as blue lines here, and you can see we've got some magnetic field lines pointing upwards and some pointing downwards here. And there's going to be interesting things happen along the boundary. A process known as reconnection takes place, and let's see what has happened to those two particular field lines. You can see they have come apart and reconnected in a different configuration. So you can have, for example, motion taking place down at the photosphere, and then the energy is released at a totally different point when field lines come close to enough to each other that they do actually reconnect. So in this area here, it's all changed, but look at the amount of magnetic magnetic tension that you will have there, tightly curved field lines, this is going to give away a lot of energy here. And it could also happen if you have a configuration like this and it is stretched, you'll see that the blue field lines, or the area between, say, the blue and the green, it's connected in this direction, it's stretched. Now between the blue and the green, it's connected horizontally rather than vertically. So energy is given out as this process. So it may be movements down at the photosphere are influencing what happens higher up. It could be that coronal loops are relevant here. Those are thought to follow the magnetic field. And one interesting problem is modeling the temperature of them. Okay, I'll save you the details other than to produce some of the results here, that we can see that we have hot loops which get up into the millions of degrees, but we also have cool loops. We're measuring temperature here, not height, and loops that we call hot-cool loops, which are hot halfway up, but they're actually cool near the very top. So there's a bit of modeling has gone into this, but we end up with some interesting results here. Well, I've talked about what happens in the outside of the sun, the various atmospheres, but how is the energy actually produced in the sun? Right in the middle, that's where you've got the energy produced. And if we take a look at this, what kind of particles do we have here? Well, most of the sun is made of hydrogen. And earlier in its lifetime, even more of it was made of hydrogen. You've got the various fundamental particles here, mainly protons and electrons, positively charged protons, negatively charged electrons. We've got the neutron, obviously it's neutral. You've got the gamma ray, well, that's energy there. You can have atoms coming together, and generally, yes, here we see some of the lighter atoms here going up to helium, helium-4, which has 2 protons and 2 neutrons. Heavier atoms such as nitrogen, 7 protons, 7 neutrons. But generally, it's thought what happens in the sun is that you have 2 hydrogen atoms are forced together. If there's enough energy, they will come up against each other. Now it looks like a slow process. It will take about 1,000 million years. If we were just to identify a given hydrogen atom, it would take 1,000 million years for it to hit sufficiently square on another hydrogen atom. But of course, there's lots of hydrogen atoms, so this is happening a lot more quickly. But when it hits another hydrogen atom, one of them effectively gives off a positron, turns into a nucleus, and you've got something that will be more efficient at attracting a further hydrogen atom. This produces light helium, gives off energy, and if 2 instances of this happen, and the 2 atoms of light helium come together, they produce a standard helium and 2 hydrogens. So what's happened here? 6 hydrogen atoms have come in, 2 have come out, 4 hydrogen atoms have been lost, but we end up with a helium atom as well. 4 hydrogens come to be a helium, but the mass of 4 hydrogen atoms slightly outweighs the mass of helium there. So under Einstein's famous equation, mass has been converted to energy. There's various other reactions that go on there, but they're on a more minor basis there. Perhaps the second reaction chain that happens in the sun, we call it the CNO cycle, because it involves carbon, nitrogen, and oxygen. That, well, we can start the cycle at any point, but if we have carbon and just more hydrogens just keep adding themselves, and it gradually becomes nitrogen back to heavy carbon, and then to standard nitrogen, light oxygen, heavy nitrogen, and then once this heavy nitrogen gets one more hydrogen, rather than forming standard oxygen, it forms standard carbon again and gives off a helium. 4 hydrogen have come in, 1 helium has come out, and the carbon nucleus has been renewed there. It's thought that this CNO cycle actually takes place in larger and more massive stars. But how did the sun reach this point? It can't have appeared fully formed. The sun would have actually formed out of, many thousands of years ago, out of a gas cloud, and there's various gas clouds that we can see. Okay, this is such a nice picture that my diagram here scarcely does it justice here, but I'm drawing attention to the fact that you could have clumps condensing in this gas cloud, and you'll see that maybe they don't quite condense symmetrically. Each of those clumps may just seem to have an element of asymmetry that will eventually lead to a bit of rotation there. But the clumps will condense, things will get hotter in the center, maybe you'll have a few minor parts coming together outside the center. Those may form planets, but eventually you reach the point where the center is hot enough that nuclear reactions can start. So that's very briefly how the sun may have formed. But eventually, and it's not going to happen for a long time, the hydrogen in the core will run out. In the core, a lot of the hydrogen will have been converted to helium, and the whole thing will, I suppose, grind to a halt, a bit of a sputter. You've still got energy being produced just outside the core, but the core condenses, it heats up, and then eventually it gets hot enough that that 3 helium atoms can come together, 3 helium nuclei can come together to form a carbon nucleus. So you've got the sun now in a red giant phase, but yes, as long as a third one comes in sufficiently quickly, you'll be able to produce carbon there. Now, that's probably where the story will grind to a halt for the sun. For larger stars, yes, the carbon can combine with more helium to produce oxygen or neon, and then further combinations would produce calcium or similar elements until you reach a point near iron where the whole thing really does take on a new phase. But as far as the sun is concerned, well, you've still got things happening in the outer parts of the sun. The outer layers will drift off, and you'll end up with a planetary nebula such as this one here. What's left in the center? Well, it'll start condensing. It'll become a white dwarf, maybe around the size of Uranus or Neptune, gradually getting fainter, but containing most of the mass that was originally in the sun. It's rather a sad story when we put it this way. But let's just finish just by looking at some of the interactions between the sun and the Earth. Okay, pretty pictures, nice cloud patterns. But the next type of clouds I'd like to mention, well, that's totally different. Here we can see noctilucent clouds, clouds high to the north of here, maybe up near the Faroe Islands, where in the summer, and it's not quite dark here, it's still daylight in the Faroe Islands, so, or at least above the Faroe Islands. So those bright clouds are in sunlight, whereas you can see some lower clouds here, which are in darkness. So noctilucent clouds, yes, have a look between around May and August. I've been able to see from the Sheffield area 2 or 3 displays per year. Hereford, okay, it's a little bit further to the south, but I would certainly not rule it out here. So as I say, a few displays of noctilucent clouds. Well, another phenomenon is that of the aurora. And the sun is directly influencing, well, when things erupt off out into space, like some of those prominences, the sun's magnetic field will perturb the Earth's magnetic field. And the Earth's magnetic field, well, because it's perturbed, various of the atoms high in the atmosphere, they'll get excited, but then eventually the electrons will move back to their normal positions, giving off energy in the process. So sometimes what you see is the sky, rather than being black or a kind of dull orangey brown light pollution color, will actually appear red or green. And it's not just in the north that this happens. You can probably see about half of the constellation of Orion here. It is possible to get aurora to the south as well. And yes, that's one that I saw during 2024. It was the first aurora that I'd actually seen since moving from further north around 1993. You've got various effects that the sun has on what we see in the atmosphere. It lights up certain features. Here we can see what's called a sundog or a parhelion. It appears as a slight spectrum 22 degrees to the right or the left of the sun. Parhelion, sometimes called a mock sun or a sundog. So hexagonal ice crystals and the pattern there, and not too dissimilar to that when we have the water concerned. Rain in one direction, sun in the other direction, you can get the phenomenon of the rainbow. So a few rainbows here. Sometimes we can just see the hint of, well, we've got the main rainbow here, just a hint of a second rainbow here, and the fact that, yes, it's slightly brighter inside the main rainbow than it is outside. And this is actually one that I'd seen just earlier this week, so I brought a picture of it along. So rainbows in the Earth's atmosphere. Now, I started with a sunrise, and I have to confess that I showed 2 things that I claimed were actually sunrises, but one of them was actually a sunset, and we'll just have a few other sunsets just to finish here. I was lucky enough to just get the sun passing behind a castle on a hill a few years ago, and I was able to just move my position by 100 yards in order to get this alignment here. But then we can also see it's the end of the day, the sun getting lower and lower into the sky. So with the end of the day, I'll signal the end of the talk. Thank you.
Thank you ever so much, Colin. What a wonderful talk. we do take the sun for granted, don't we? I mean, it's the giver of life, of everything really for us, but what a fascinating object it is. Um, I'm happy to say that we haven't got any blinded members in our society, although Donald Trump did his best a couple of years ago, didn't he, to ruin his eyesight. Let's hope he tries again. That's all I can say. Yeah, wonderful. We always have a tradition with um, our online Zoom meetings of showing our appreciation digitally as well as visually. My fellow members are sick and tired of hearing me say this, but I have to explain it to each new presenter as they come along. So can I ask everybody, first of all, to show in the traditional way now our appreciation for such a wonderful talk from Colin. Thank you very much. There you go, a mixture of claps to the camera and digital claps and both. Thank you, Colin. That was wonderful.
No, that's much
Really
appreciated.
enjoyed it. And also in keeping with tradition, I'll just kick things off with a very quick question, then hand over to the floor. Going right back to the beginning, the sort of onion ring aspect of the sun, these three so-called atmospheres, as you peel them back, you explain very clearly how they are described, how they the temperatures and the various constituents. But this thing between the first and the second, which I think is I've got it right, the photosphere and the chromosphere. My little Greek tells me that photo, of course, means light and chromo means color. To take one of your thought experiments again, if we could peel back that middle atmosphere of the chromosphere, which gives the sun its yellow-orange color, presumably, what would we see with the photosphere? I mean, would it be white or would it be, I mean, what is the distinction that's really being made in not in terms of temperature or what's going on in nuclear terms, but what is going on in terms of light between, I'm struggling I mean, I'm assuming the photosphere isn't invisible. It does give off light, but how does it differ from the color and the light from the chromosphere?
Yes, I mean, generally what you've got is something called Wien's law, or Wien's law, that relates for one of the strangest named astronomical objects, the theoretical black body, which is effectively giving off pure light. That if you do the maths on that, you'll find that the hotter an object is, the shorter the wavelength of the light that's coming out. So if you've got the sun's photosphere, where the light is being emitted from, a lot of it is absorbed by the chromosphere. But if you're thinking in terms of the light, the translation between the temperature and the light here, yes, you'd have that the maximum, the wavelength of maximum intensity would be longer for the chromosphere than for the photosphere. So it could well be that, yes, yellow for what we see, what the chromosphere has done to the light from the photosphere. But as I say, peel it back. I'm not going to claim, of course, that if the maximum intensity of the light occurred in the greener part of the spectrum, that it would be green. It doesn't work that way because there's bright colours both sides of green, but it could well be that it would appear whiter. So, I mean, examples, Sirius, Procyon, some of the nearby stars that they're just that little bit bigger and brighter than the sun. And more relevantly, just that little bit hotter, they appear whiter.
Yeah, and then you go to the blue-white stars, the very hot ones.
The very hot ones, yes.
And the red supergiants being cooler, appearing red. Yes, I understand.
Yes, yes, the red supergiants and the red dwarfs. Wien's law tells us that, yes, the phrase red hot in a domestic setting would appear to be quite extreme, but it's only really the beginning of the situation.
Yes.
I mean, I suppose being in Sheffield, they do have the Magna Centre that you can go off to and just see various the heritage of the various industries that took place there, where things would become white hot rather than merely red hot.
Yeah. Okay, thank you for that. And just briefly on the aurorae, I'm one of those unlucky people. I've never seen an aurora. I'm hoping to, but I'm too lazy, I think, and they're so unpredictable, aren't they? The number of times I've woken up in the morning and then listened to the morning news, and they said people were treated all over Great Britain to a wonderful sight last night, as far south as Hampshire and Dorset and what have you, and South Wales, and I never see the damn thing, but lots of our members have, and some of them have taken wonderful photographs as well. So that's still on my bucket list, I'm afraid.
Well, yes. I mean, obviously, this sounds like I'm being paid by the Scottish Tourist Board, but you increase your chance by going there, or in more extremely going up to Iceland or places. But it does seem a long way to go for this kind of thing. But sometimes it's a case of there are a few little apps and networks and things that my experience is that 90% of the time when there's an alert on those apps, it doesn't come to anything. But it's certainly worth a look. And I think we did have three. Yes, there was the one around May, which it did seem to be reasonably well publicized. But I also saw one in August. I was really looking at meteors and taking pictures, and I noticed that yes, I was getting a purplish glow. And then when I just decided, well, rather than observe to the southeast, I would observe to the north, and I was getting a much stronger purplish glow. It wasn't coming up naked eye, but it was certainly registering on the camera.
Very good. Yeah, my daughter and her boyfriend went to Iceland last year, and cost them a pretty packet, and they went to go whale watching and aurora watching, and I am slightly comforted by the fact that they saw neither. So
I mean, as I was saying, yes, it's a bit disappointing when you go on what's obviously a major expedition and you don't get a great deal out of it. I did see that there was a comment came up, and presumably is in the chat about, I think it was a specific app being mentioned here.
Yeah. Yes, I'm just looking at that now. App Aurora. Yeah. Okay. Right. Thank you, Katrina, for that. Right, I'm going to hand over. Who's got a question for Colin? Please.
Throw one in.
Thank you, James. I knew I could rely on you.
With the various zones within the sun, the various parts of that onion shell, are they fairly distinct, or is it just a gradual change from one to another, or is it very difficult to tell?
Right. I mean, as far as, and I'll get a quick zoom back through the beginning, pun not intended there, but it depends which ones you are considering. That if you've got, I mean, the photosphere itself is quite thin. I mean, if you think in terms of 500 kilometers out of a solar radius of the best part of 1 million kilometers, I think you're talking about things happening quite quickly here. But yes, I mean, if we look at the the border between the convective zone and the radiative zone, you're talking about, they owe their distinction to the kind of processes that are transporting the heat there. And yes, there will be, I'm not sure I'd like to put a figure on it, but there would be a more substantial zone where you did have a bit of a transition zone. It could be that over many thousands of kilometers you've got more of a transition there. And also you've got the fact that as the sun grows older, the characteristics of the core may change, and just change the model there slightly. And then further up, where the chromosphere becomes the corona, again, I suppose people are obsessed with trying to put figures onto things, but it might not be very meaningful to do that.
Yeah.
So I think what I would say, it just depends which transition it is that you're looking at.
Mm-hmm. And that's driven by what, temperature gradients or any?
You've got temperature gradients, yes. You've got things like the equivalent of I say that you've got a majority of plasma, but what the ratio of mass of gas to plasma, all sorts of, well, they call about the recombination of the plasma into a gas, all that kind of thing influences just what kind of what kind of the of process you have there. I mean, heat will radiate if the matter is transparent at that temperature, but depending on how the recombination is going, that figure could well change.
And the fusion zone is purely the core, or is it also come out further?
It is the core. Later on in the sun's life, you might have, for example, helium being fused to form carbon in the core, but then outside the core, you would have another layer where there was still hydrogen that was being put together to form helium, and so on. I suppose at that point, you would have several layers of core, just depend. I mean, we're playing with the definitions by this point, but at the moment, yes, the fusion is combined. It is confined to the core. You do get high temperatures up in the corona, but you don't have the same pressures there.
Right, okay. And finally, with the fusion of different heavy and heavy elements, are they each at different temperatures, or is it same very high temperature for all the different fusion reactions?
You would find that the more energetic ones, the helium to carbon, the triple alpha process, that will cause a hotter inner core. And for those stars that are capable of doing it, the ones where you're fusing things to produce atoms near iron, then that's going to produce even more energetic ones and hotter ones. But of course, many of those stars, you've got many layers. So if you've got a red giant, because the red giant is so big, then the initial temperature is spread out over a much larger surface area, which actually tells you that although you've got a fairly cool edge, your center could be even hotter than the standard star.
Thank you.
All right. Somebody else? Another question?
A question about the cycles, Colin. I love those butterfly charts that showed how the spot activity sort of migrates from north to south or from the equator to the poles. I had in my head that there was a 22-year cycle, not just
yes.
But is that
yes, I mean, if we can...
reversing?
Sorry, I should let you finish your question.
No, I'm just musing. Is that just the poles revert to where they were 22 years ago?
It is, yes. I mean, what happens is that, let's just look at this one that I've shown here. After one revolution, the equator has run ahead of what's actually happening for the higher latitudes. If you imagine after a year or so, you'd have the magnetic field wrapped all the way around, and after about 5 or 6 years, it would be wrapped even more wrapped several times round the equator. It's a bit like what happens when you just take an elastic band and just start rotating one of the fiber at one point. It gets very tense, and suddenly it'll a bit will stick off to the side. That's how the sunspots are thought to be produced, some equivalent to this. But then, yes, and it seems when it collapses towards the end of the solar cycle, it actually, you could say, it overshoots. So you end up with for the next cycle, everything is actually reversed. So in terms of what's actually repeating, it is a 22-year cycle. But in terms of the magnitude of that, which is what manifests itself in the sunspots, that's 11 years.
Okay. Somebody else with a question? Or are we done?
Colin, you asked about, you talked about the radiation going through the radiative layer taking a long time because it keeps being absorbed by matter, which presumably means that the atoms and molecules are relatively close together.
Well, yes. I mean, you've got a lot of pressure in that part of the sun. Yes, high pressure, high density. So it's not long before it gets absorbed by another atom, and it can actually be sent off in a different direction, and it can have stages where it's going further back. A particular heat parcel is going further back in towards the center, just because there is so much matter there.
And so high density, would that be the sort of density we'd expect from a solid or from a liquid other than gas? I mean, not appropriate terms.
In a sense, under very high pressure and density, the distinction between them actually becomes a little bit less clear. For example, you talk sometimes about metallic hydrogen. That, yes, hydrogen is off on the left-hand side of the diagram, so there are times that it would stop exhibiting gaseous behavior and start metallic behavior, similar to, say, lithium or something there. So, yes, temperature would tend to send the matter up the states, towards gas and then plasma. Pressure density, they would tend to put it down the other way. So you've got a bit of a balance there, but certainly very dense.
Am I thinking right that the overall density of the sun is just a little more than the density of water?
That is true. The Earth has a density of about 5.5 times that of water. And the sun has a volume of a little bit over 1 million times that of the Earth, but a mass of about 340,000 times that of the Earth. So I suppose if you take the Earth's density and divide by about 3 or 4, you end up 1 point something in terms of the density of water. So that's perfectly correct. But some of the outer layers may be significantly less dense. The density profile varies quite tremendously. Very dense near the centre, and then out towards the outside, not that dense at all.
Thank you.
Great. Have we got anybody else, or are we? I think we're wrapping up, are we? Okay. Well, Colin, once again, thank you very much. I'm particularly touched by the fact that I think you've achieved a first with as a Scotsman, a displaced Scotsman in Yorkshire, talking to Herefordians, or in my case, an adopted Herefordian. You took the trouble to tell us what was happening during a solar minimum in the mid-17th century in Hereford, and I think you're the first person ever to actually sort of localize the talk and actually take into account where your audience and where you're speaking to. So thank you for that. But no, on a serious note, it was a wonderful talk, very entertaining, very informative, and thank you very much indeed. So once again, everybody, can I ask you to give your reactions and show the usual appreciative round of applause. Thank you, Professor Colin Steele.
Much appreciated. It's been good to have made everyone's acquaintance tonight. Yes.
Yeah. Well, I noticed through Astro Speakers, I found you, and I found you elsewhere on the web, and you obviously have a whole catalogue of talks. So perhaps in a future season we could invite you back again. We'd love to have you back again.
Well, yes, that would be nice. Yes.
You'll have a bit to go to beat Steve Barrett. I think he's on number 4 now with us, but there's room for plenty more anyway before Steve dominates it all. Okay, thank you, Colin. Thank you very much indeed. Unless anybody has anything else, we'll call it a wrap. And I will.
You going to go over something, Chris?
Sorry, yes, go on, go ahead.
Weren't you going to go over what was it you said you were going to 5 minutes at the end? Cover what it was you said at the beginning.
Well, I was going to just briefly show something from Stellarium about. It's a little bit late now. I think I'll leave that for another time. It's I think we're done. That's all. We'll talk again. We've got incidentally, James there, who was asking some of the questions, Colin, through his employers has got us a pitch in Hereford to watch the upcoming, you mentioned the upcoming partial eclipse on the 28th, is it?
29th.
So we're all, there's a
yes, it was Saturday morning. So,
yeah,
yes.
So we're hoping some passers-by. There's going to be, it's actually a garden centre, so we're hoping there'll be some shoppers around and we can grab hold. And we've got plenty of legit glasses as well, observing glasses. So we're hoping we can pull in a few people, and who knows, maybe gain a few extra members courtesy of the sun. So
yes, I mean the sun is often a good one to take to the public rather than having them blundering around in the dark and whatever. Well,
we're looking forward to that. And then there's a group of us also going off to for a trip in midsummer. We'll talk more about that amongst ourselves. But in the meantime, thank you, everybody. I will see you next month. And it is the aforementioned Steve Barrett at the Kindle Centre. But in the meantime, thank you once again, Professor Colin Steele, and good night, everybody.
Okay, thanks so much. It's been good to have been there. Yeah.
Bye-bye.